Hello, let's talk about internal forces of beam problems. Alright, please recall the actually loaded members and the torsional members. In the case of actually loaded members, the internal forces were what? The tensile force or the internal compressive force. So make sure that the internal forces are the stress resultants. So if you integrate the stress or traction acting on the surface of a cross section, then we can obtain the internal forces. That's why I emphasize you several times that the nature of internal forces are nothing but just the correspondence of the stressed field at working on the cross section of your free body diagram. In the case of torsionally loaded members, the internal forces is called torsional moment, which is integration of a contribution of small shear stress over the cross section. Then if you integrate the contribution of small torsional moment over the cross section, we can obtain the torsional moment acting on the cross section. Okay, so now let's focus on our beam problems. Now we want to define the internal forces. So, saying again, we need to figure out the stress field, and then integrating the stress field, and then we want to express the resultant of stress field in certain form, which is called the internal forces. The internal forces in 우리말, actually we encountered several times. In internal forces in 우리말, because 내력. Okay, 내력, internal forces. Alright, so now let's consider simple problems to visualize to explain the nature of internal forces using cantilever. So let's consider a cantilever. The cantilever means the one end is fixed. Here the one end is fixed. So at this point, rotation of the beam and the transverse displacement, they both are equal to 0. So as I told you, do you remember there are 2 degrees of freedom regarding beam members. The first one is transverse displacement. The second one is what? Second one is a rotation of a certain point of that point. So in the case of cantilever, so this end is fixed against any deformation. So there is no transverse displacement and no rotation at this point. And then we have a free end here. The free end, at this free end, we want to consider 2 different kinds of external loads. So I want to consider one concentrated load and the moment load in here to consider general load conditions. Okay. So here we want to consider the cross section where we want to check the force equilibrium. Because the overall system is in a static condition, is in static equilibrium, and then even if we consider this small segment of the beam must be in the equilibrium status, isn't it? So now let's consider, let's zoom in this small part here. So we're gonna consider the bigger part, such that here we're gonna check the force equilibrium condition to be satisfied in the sense of force equilibrium. So as I told you, on the right hand, on right hand side, we have 2 concentrated load here. So first, let's consider the force equilibrium in the vertical direction. So because this is 2-dimensional problems, we have to consider 3 kinds of force equilibrium. First one is let's put a coordinate. For example, let's introduce a coordinate for our analysis. This is x direction and this is y direction. And depending on authors, instead of x, sometimes we call it x1, and then instead of y, we call it x2. Okay, the same meaning. So using the initial rotations are beneficial if you want to code this procedure in computer. So if you use index, then you can use do loop. But if you use x and y variables, then we need to use separate variables depending on the direction of the coordinate system. The initial rotations are preferred in the computational mechanics. Anyway, this is the definition of the coordinate. Here, once we introduce the coordinate system, so we need to satisfy the force equilibrium in x direction here, and also we need to satisfy the force equilibrium in the y direction too, isn't it, right? And also we want to check the moment equilibrium, So because of the symbol, and then it should look like this. So we want to consider the counterclockwise direction is positive. So we can check three different kinds of equilibrium condition. Okay, let's check one by one. In the case of force equilibrium in the vertical direction, here look at this. Because we want to check the force equilibrium in the vertical direction, we need to identify the external forces, all kinds of forces acting in the vertical direction. The first one, which is a really apparent one, is the external force. External force is acting in the vertical direction. And then to satisfy the force equilibrium as given here, so we need to have some kinds of traction on this cross section of this free body diagram, isn't it? Otherwise, we cannot satisfy the force equilibrium. To satisfy the force equilibrium, we need to have this traction on this surface, isn't it, right? So it is pretty clear that there should be certain distribution of shear stress on this cross section. Otherwise, we cannot satisfy this force equilibrium. Okay, so now we can agree that on this cross section there must be shear stress distribution, isn't it? So next step, we want to check the moment equilibrium. And then here, now I understand we are pretty sure that we have the shear stress distribution here to satisfy the force equilibrium. So let's check the moment equilibrium. So if you check moment equilibrium, and then we need to count all the moment. So we have one external moment in the clockwise, and then if you choose a reference point here to calculate the moment caused by the external load P, then it also produces the counterclockwise moment. Then we cannot satisfy the moment equilibrium condition, which is given here, sum of moment is equal to 0. Then how do we satisfy the moment equilibrium? To satisfy the moment equilibrium, we have another moment. For example, because of the external force, we have non-zero moment in this direction, isn't it, right? To cancel out this moment, so we need to have another moment in the opposite direction. Otherwise, we cannot cancel. We need this moment. So how do we produce this moment? So to produce this moment, we need to have some kinds of stress distribution in this normal direction. Okay, that's why we can understand that yes, there must be a certain distribution of normal stress field. Okay, to satisfy both the force equilibrium in the vertical direction, the force equilibrium regarding the moment. Okay, so next step, let's check force equilibrium in the horizontal direction. So make sure that there is no force component in the horizontal direction. If you look at these external forces, no external force in the horizontal direction, which means for this free body diagram, so if you check the sum of all the forces in the horizontal direction, then its net sum should be equal to 0. Which means at first here we assume that the direction of normal stress in the left hand side, but to satisfy the force equilibrium in the horizontal direction, we can easily understand that the direction of normal stress is not in the same direction, but the direction of the normal stress changes within the cross section. So some part goes to the left hand side, and then the remaining part should go into the right hand side to cancel to make all the forces in the horizontal direction is equal to 0. Okay, summarizing, to satisfy the force equilibrium in the horizontal direction and the vertical direction and the moment, so we need to have a certain distribution of shear stress and a certain distribution of the normal stress here. But regarding the distribution of normal stress, its direction changes within the cross section. The situation is pretty much different from the condition found in actually loaded members. In the case of actually loaded members, the direction of normal stress is the same, whether it stretches, whether it compresses. But in the case of beam problem, this part compresses the material, and this part stretches the material, which means according to sign convention that we already introduced for the actually loaded member, according to that, the normal stress is positive if it stretches the material. The normal stress is compressive, it compresses the material, isn't it? Negative if it compresses the material, isn't it? But in the case of this beam problem, so we have both of a positive stress and a negative stress here in the same cross section. That's why for the sign convention of moment, in the case of the axial loaded member, the sign convention of internal forces was exactly the same as sign convention of normal stress. But in the case of the beam problem, the sign convention of moment cannot be same as the sign convention of normal stress, because the moment is a representative value of the cross section. Because we can here, for example, to check the moment equilibrium for this moment, so we have to integrate the moment contribution of normal stress. But the sign of normal stress changes. Some part is positive, some part is negative. That's why we need to develop its own sign convention for the internal moment. Is it clear? Okay. That's why we need to have a new definition of the sign convention for the internal moment. Okay, so now let's define the internal forces of beam problem. So as I told you, there must exist shear stress on this cross section. So if you integrate the shear stress over the cross section, then we gonna call that resultant internal shear force. Okay, internal shear force. In 우리말 it is called 전단력. Some people say 내부 전단력. Okay, 내부 전단력. And then if you integrate the normal stress, so if you integrate normal stress, in the case of beam problem, the pure beam problem, the integration is equal to 0. The internal actual force is equal to 0. This is characteristics of beam problem. And then if you collect all the moment contribution caused by this normal stress, the moment, how do you calculate the moment contribution? The moment contribution is the force times the arm length. That's the moment, isn't it, right? So arm length is given by the y coordinate. Let's say, by the way, I forgot to introduce a coordinate system. So let's put a coordinate system here, x and y here. So the place where we introduce the origin of the coordinate system at this point, so we call it neutral axis. In 우리말 중립축. So we'll discuss the meaning of neutral axis later. Anyway, at this moment, but not later, maybe next week. Okay. So at this moment, please understand that we have neutral axis at the origin of the coordinate system for our calculation. And then make sure that this is the arm length for moment contribution, moment calculation. And then we need the force. Because normal stress is not the force yet. So we need to multiply the cross-section area to the normal stress. That's why we multiply this cross-section area to the normal stress value. And then if you integrate it, we can obtain the moment. And this moment is called moment. 힘 in 우리말 힘 moment, or according to some people we call it 내부 힘 moment. Anyway, so which means make sure that in English we have internal, okay, the adjective of internal. So that emphasize they are not external forces or external moment, but we are talking about the internal, internal shear force and internal bending moment. Okay. So now let's choose the sign convention. As I told you, we already have the sign convention for the normal stress. For the normal stress, if the stress, the traction stretches this material, then we're going to call this positive. If the traction compresses the material, so we call it negative stress field, isn't it? But as I told you, in the case of the beam problem, even in the same cross section, we have positive normal stress and the negative normal stress here. That's why we cannot use the same sign convention as for the material point for the normal stress. We have to devise a new sign convention for the bending moment. For bending moment, here the sign convention is very, very easy. Let's say we have a coordinate like this. Let's say we have a coordinate, and then the sign convention is if any internal bending moment, if any internal bending moment produce a positive curvature, okay, for the choice of coordinate system. So we define it positive bending moment. We're saying again, let's say we have this bending moment, then it makes the segment of our beam segment would deform like this. Okay, it can make convex upward. Okay, convex upward. So that produced the positive curvature. So we want to define this positive bending moment. Is it clear? So once we define the positive bending moment, the next step is we want to define the sign convention for the shear force. Okay, shear force. Okay, so now we have a positive definition of positive bending moments. So now let's introduce a coordinate system here. So if you introduce coordinate system, and then once we introduce coordinate system, so we can measure the size of segment by dx. Okay, let's say this surface is x, and then we have dx. Because we have change of distance by dx, then there must be change of bending moment too, isn't it right? dm. Let's say we have positive bending moment. Okay, then with just bending moment, there is no way to satisfy the force equilibrium for this bending moment, isn't it right? Then how do you satisfy the force equilibrium? Then let's say we have some kind of shear force. For example, I have shear force upward and the shear force downward. Then that satisfies the force equilibrium in the vertical direction, isn't it right? Or we can consider this combination too. But if you look at these guys carefully, and this guy produce bending moment in this direction, isn't it right? Because if you choose a reference point here, it produces bending moment in this, not bending moment, the moment in this way, the clockwise. And if you look at this guy, and that produce moment, counterclockwise, isn't it? So in the case of this one, which one can cancel, the change of positive bending moment? This guy or this guy? Yeah, this guy would cancel, the positive bending moment to satisfy the force equilibrium condition. Okay, so the pair of shear force which conforms to positive bending moment is defined as positive shear stress. Okay, positive shear stress. So the definition is here. This is way of what I explain is the way of understanding why they choose this shear stress as a positive shear stress field. Okay. The definition of the internal bending moment, sign convention bending moment, is given here. The bending moment producing, as I told you, a positive curvature is positive, and then if it produces negative curvature is negative. As I told you, the sign convention for the shear stress was determined by the sign convention of bending moment. We introduced sign convention for the bending moment first, and then depending on the the equilibrium of the moment field, then we can determine this positive default sign convention for the shear stress field, shear force field. Sorry, the positive shear force couple that produce moment. Okay, produce a positive change in the bending moment. Okay, this is my definition. And the negative shear force couple produce a negative change in the bending moment. Okay, this is the sign convention for the bending moment and the shear force. Once again, the sign convention for the beam problem, the internal forces of beam problem, must be different from the sign convention of internal forces of actually loaded members and torsional members. The main reason is what? If you consider cross-section of beam, the sign of normal stress changes within the cross-section. That's why we cannot follow the same sign convention for the definition of the sign convention of bending moment and shear forces. That's why we introduce new kinds of sign convention for the internal bending moment and the shear force. Okay, that is the reason. The starting point is we wanna choose a certain moment pair which produce positive curvature in our choice of coordinate system. So once you choose the positive moment, then we can determine positive shear force couple which produce a positive change in the bending moment. Okay, that's how we determine the sign convention of internal bending moment and the internal shear force. So if you have any questions regarding the internal forces of internal bending moment and shear force, please let me know. So I'm very happy to explain you what I know. Okay, so let's start my lecture here. We just defined the internal bending moments and internal shear forces. In the next video, we're gonna talk about how we calculate the change of shear force and change of bending moment subjected to the external force conditions. Here, let me start my lecture here, the first part.